Hi, welcome to educator.com. We're going to be looking at shape again, but now we're going to look at calculating skewness and kurtosis. We couldn't do this before when we covered shape because you needed to know something about variability first. All right, this is the roadmap. Basically, we're going to be covering skewness, the concept, right? And then we're going to try and connect that to calculating skew. Then we're going to talk about how to interpret that number that you calculated, and also what that number will tell you about the relationships between measures of central tendency. Now, obviously, because the number directly relates to actual concepts of skewness, it'll also, these measures of central tendency relationships will also hold for the skewness concept. Then we're going to talk about kurtosis. Kurtosis is often something that people don't focus a lot on. Mostly because it's a sort of difficult shape to understand. We're going to talk about calculating kurtosis and how to interpret kurtosis. All right, so first let's start with the concept of skewness. Now we've been over this again and again. We know that there are skewed right distributions, skewed left distributions, ones that aren't skewed at all, right? So there's lots of these distributions, right? This one's not skewed. So anything that has a tail is sort of skewed, right? These are also called J shapes. More formally, they're called asymptotic shapes because there's sort of this asymptote right here. It asymptotes against the x-axis. So skewness, we know it means that there's a tail of some sort somewhere. One side is longer than the other. So one side has values that go on, and those values aren't clustered around other values. So that's basically the concept of skewness. Now, it would be nice if we could get a number that would tell us, oh, this is exactly how skewed your distribution is, right? So a distribution like this might be somewhat skewed, right? But a distribution like this might be really skewed, right? So it would be nice if we could say how much more skewed one is than the other, right? And so skewness, what we're going to calculate, is going to tell us exactly how skewed something is. On the positive end, it'll mean that the tail is on the right. So if the number is positive. If the number is negative, it'll tell us that the tail is on the left. And the greater the positive number, it means it's more skewed on the right. Normal distributions often have zero skew. So things that are symmetrical often have zero skew. All right, now let's talk about calculating skewness. Now some people get a little bit freaked out at this, but everything here, I want to boil it down to like what's important. So here's the main heart of the skewness function. Basically, it's going to be the sum of cubed distances from the mean, right? And we'll talk a little bit about why it's cubed. So the sum of all the cubed distances of each point from the mean of the sample. But instead of sum of squares, it's the sum of cubes, right? Over the standard deviation that we've, the standard deviation little s, where we use the sample to calculate the standard deviation of the population to estimate it, cubed, right? That's basically the crux of the idea. Now, there's going to be some more frills on this, but this is basically the heart of the idea. And let's think about why it's cubed. It's cubed because it's going to matter whether it's positive or negative, right? Before, when we squared things, we didn't care which direction away from the mean it was. But now we care. How far are you away from the mean? And by cubing it, how far are you away from the mean? but also what direction are you away from the mean? So now we're having things that are stacking up. It's like each little point is having a little vote. They're saying, I'm on the left side, I'm on the right side, I'm on the left side, I'm on the right side. And by adding them all up, we see who wins, the left side guys or the right side guys, right? When there's more guys on the negative end, we get a smaller number, right? So a very, very small number. When there's more guys on the positive end, we get a large number. And by cubing it, what we do is we make those that are on the ends matter more than those that are sort of close to the center, right? Because cubing is going to make it much bigger than squaring, right? And so that's sort of the main heart of the idea. And just to review, if you double-clicked on this S, what would be inside, right? So think about like clicking on that S. What would S be equal to? Well, S is really the the sum of squares divided by n minus 1. So because it's the standard deviation, we would square root that. And so that's what this is. Now, standard deviation is always going to be positive, so this isn't going to change its sign, right? Now, on top of this skewness, the heart of this function, sometimes people divide by n as well, right? Or n minus 1, right? In Excel, it's going to multiply by n times n plus 1 divided by n minus 3, all this other junk, right? But that junk sort of doesn't matter because that's not going to have as great an impact on skewness as the heart of this function, right? And so that's what I sort of want you to know. This is sort of the heart, right? Looks sort of like a heart, right? So that's the heart of the function. And the other stuff is just frills. Okay, now this is one type of skewness, but there's actually a ton of different types of skewness. There's Pearson skewness, and there's lots of skewness that I can't remember the name of. Minimal skewness or something distant skewness. There's momentum skewness. There's a ton of them, right? So if you want to know more about skewness, you could check out this link. It's Math World by Wolfram Alpha, and I frequently use it and refer my students to it. All right, so now let's talk a little bit about interpreting skewness. So imagine this is all of the skewness values that are possible, right? If we find out that something has negative skewness, like let's say it has -1 skewness, right? We find out that a distribution has it, but I haven't shown you the distribution. Can you guess what kind of distribution it is? Yes, you can. You know that it must have some sort of tail that goes to the left. On the other hand, if it's a positive one, you know that it has a tail that goes to the right. If the skewness is 0, sorry, this is a little bit askew, but if it's a 0, we're not sure exactly what it is, but we know that it basically looks symmetrical, right? So it could look uniform. It could look like approximately normal distribution. It could be some other crazy thing that is symmetrical, right? Right? So it could be any number of distributions as long as they're approximately symmetrical. So now let's talk a little bit about how to look at skewness in SPSS. So go ahead and download the example Excel file. And basically, if you look on the first sheet, it should say skew data. I've shown you 3 different little data sets. Data set A is skewed to the right. Notice that it has a tail to the right. Data set B is skewed to the left. Notice that it has a tail to the left. Data set C is more normal. It's more symmetrical, basically. So it has a little peak here, but it's roughly symmetrical on both sides. Now, the nice thing about Excel is that it does have a skew function. So you could automatically generate skewness. And the skew function is just skew. And you put in the data that you'd like it to calculate. And this is showing you a skew of 2.0 2.08, 2.09, basically saying that it's very, very positively skewed. Now, I could just drag this across, and it'll calculate the skews for the data sets above. So this one is for this data set, and we find it's a negative skew, almost as negative, so the extent is almost as negative as this one, right? So this is about +2, this is about -2, and it's because these two are largely mirror opposites of each other, so they have similar skews. Here we see the skew is closer to 0. It's still sort of on the positive side, but it's closer to 0 than it is to, 2 or 3, right? All right. So SPSS, if you're interested in the particular formula that they use to calculate skew, you could double click, and when this little, it's like a little helper window comes up, you'll notice that skew is a hyperlink. If you click on that, then you should get this little window that comes up. That's an Excel help window. Let me make this bigger. Here they show you the exact equation that they use for skew. Notice that this part is exactly what we talked about. It's that distance away from the mean cubed over standard deviation cubed, right? And so that's all sort of the heart of the function. But here we have this extra stuff, n over n-1 times n-2. So you could use that, you could use something else, you could use 1 over n-1, that's also very common. I'll be using 1 over n-1. All right, so if you hit enter, let's look a little bit first, before we calculate skew for ourselves, let's look a little bit at what it would mean to our measures of central tendency to be skewed right or skewed left. So let's calculate the mean. So mean is average. Sometimes I type in mean and Excel's like, eh. I'm going to close my parenthesis. Let's also get the median while we're at it. And let's get the mode. Once we have those three values, I'll move this up a little bit. Once we have those three values, we could actually just copy and paste straight across, and it'll find the respective mean, median, and mode for each of these other distributions. Now, let's look. When it's skewed to the right, and there's a very positive skew, what we find is that the mean is greater than the median, which is greater than the mode, right? And that makes sense. The mode is probably going to be on the very, very left side of the distribution. And the mean is highly affected by outliers, and the outliers are on the right, so the mean is going to be greater. For negative skewed distributions, we have the exact opposite pattern. This time, the mode is the greatest, followed by the median, then the mean. Remember, the mean, highly affected by outliers. This time the outliers are small, so the mean is being pulled to the smaller side. The most frequent numbers are up on the higher end, and that's why median and mode tend to be bigger. And so when you know the skewness, you automatically know sort of the relationship between mean, median, and mode. On the other hand, when distributions are largely symmetrical, when there's very little skew on either side, then what we see is that the mean, median, and mode are often very close to each other. Sometimes they'll be exactly the same. This time they're just very, very close to each other. And that makes sense because the skew is a little bit, because there is a little bit of skew, it's not exactly on top of each other. Now let's talk about how to calculate skewness. So here I've put the formula for skewness. Also, another way you could write this formula, let me insert another row here, because sometimes people aren't comfortable with sort of moving around that sigma sign. It's sort of like, where should I put it? Where does it go? that sigma will affect some things and not other things. That sigma will affect anything that has an I next to it. Because of that, you could put sigma and put the divided by standard deviation cubed in there, and it won't affect it very much. You could either do this part after you add them all up, or you could do it before you add them all up. It actually doesn't matter because of the law of distributive property. Yeah, distributive property. So you could either put this inside of this, or you could take it out. It sort of doesn't matter. So let me show you a way that you could write this. Actually, this might not be helpful to write it on Excel. I'll write it when we go back to our PowerPoint slides. All right, so let's start with this. We know that we need to get all of these distances away from the mean, right? So let's start with that and cubing that. So I need to start with an equal sign, and I'm going to put in a parenthesis to say take my value, subtract the mean, which would be the average here, and I'm going to put in all of these values. Now, I don't want that average to jiggle around, so I'm going to lock that data in place. And because I want to copy and paste it later on, I'm actually going to even leave, I'm going to leave the A to vary, but I'm going to say lock the 4 down. When I copy down this column, it won't change the A column, but when I copy across, it will change it. So I only want to lock down the number row. Then I'm going to close that parenthesis and cube that value. Now here I could also divide by this as well, but I'm just going to do this for now. So this is just the part where I'm doing x minus x bar cubed. That's all I'm doing in this column. So I'm going to go ahead and copy and paste that all the way down. And here what we have is just this part, but now I need to sum them all up and divide by s to the 3rd power as well as n minus 1. So I'm actually going to modify this to make my formula a little bit simpler and have n minus 1 down here. All right, so here you could see now I need to add these up and also divide by n minus 1 times standard deviation cubed. So here, let's do that. Let's sum these guys all up. And then divide by count, so count my data, minus 1, right? And then also multiply that with standard deviation of my data cubed. It's a lot of parentheses, right? And because it's color-coded, I know I need one more blue one to signal my denominator. And I'm going to hit enter. And there we get a skewness. I get a skewness of 1.84. That's quite close to the 2 point something that we got using the Excel function. The Excel function, it just multiplies by a slightly different constant. So that's the only difference. But once we have this, we could actually copy this over here. And so here, if I double click on this, it shows you that it's using the C column because I had let C vary, and so it's being relative about the columns, but it's locking the rows in place. And so I could also check down here. It's using the C column to count those data and also get their standard deviation. And what we find is negative 1.7, which is pretty close to the negative 1.9 or so that we found with XL's function. And then I'm just going to copy and paste all of that again to our approximately symmetrical one. And we get something quite close to the 0.44 that XL gave us, 0.39, right? And so that's how we're going to calculate shape here. One of the features is skewness. All right, so that's skewness. Now let's talk about interpreting kurtosis. Oh, I actually said that I would talk a little bit about where the skewness stuff goes. Let me just draw it over in this corner. So I'm not going to need all this room for kurtosis. So let me just talk a little bit more about the skewness function here. The formula for skewness, as I said before, is going to be the sum of all the cubed distances over, some constant and s cubed, right? I said that that's the idea. Now, sometimes you might see this formula written more like this, with x sub I minus the mean cubed over s to the third power. Now, this and this, they really mean the same thing. It's just different ways of writing it. This actually only affects things that are affected by this I. And because this is not affected by the I at all, I mean, s cubed will be the same whether it's for the first value or the last value. It doesn't actually matter whether you write it inside, included in that big sigma or not. Another way you could write it is also 1 over s cubed times x sub I minus x bar cubed, right? So this is yet another way you could write it. And so all of the three ways of writing it are equivalent. It doesn't change anything. And so don't get tripped up if you see one of these other options. They're not trying to be tricky. All right, now let's talk about kurtosis. So kurtosis as a concept is sort of weird for people because this is not something that we're used to dealing with in regular shapes. Like we know roundness and we know like squareness, but kurtosis is something a little bit different. Kurtosis is really about two things sort of bundled into one. One is pointiness, right? Peakedness. So very kurtotic shapes might look something like that. Super non-kurtotic shapes look something like that. So one important aspect of this is the pointiness, right? Peakedness. But at the same time that peakedness is going up, what you're seeing is the tails becoming thinner, right? So peakedness and thin tails usually go together. And kurtosis is about both of those things because here we not only have no peakness, but we also have fat tails. The tails are just as fat as that lack of peak in the middle, right? And so something in the middle might look something more like that, right? So this is a kurtotic sort of dimension where you're getting increasing kurtosis. And when you have increasing kurtosis, it means two things simultaneously, having more peaks, but also having thinner tails. All right. So now let's talk about calculating kurtosis. So kurtosis, let's talk about the main heart of the idea before we get into things. Like skew, you could multiply constants to it. It sort of doesn't matter. This is the heart of kurtosis. Here's my sigma. It's going to be that same distance for each point away from my mean. But instead of cubing it, we're going to raise it to the fourth power. Now, when we raise it to the fourth power, we know that we do not care about whether it is on the left side or the right side, right? So that's one thing to note already about kurtosis. It's not counting how many are on one side versus the other side of the mean. So kurtosis already, we know it'll probably be positive because it's going to raise everything to the fourth power, and when you raise something to an even numbered power, it's going to be positive. And then we're going to divide that by s to the fourth power, standard deviation to the fourth power. Now, once again, this is going to always be positive. Standard deviation is already positive, and then we're going to raise it to the fourth power. So kurtosis is largely going to be a positive number. The only difference between different values of kurtosis might be whatever constant they decide to multiply by. Frequently, n minus 1 over n minus 1 is one of the constants. I forget what Excel does. Excel does something else crazy. We'll figure that out when we get there. But once again, even with kurtosis, you could write it in a number of different ways. You could write it as 1 over n minus 1 times s to the fourth power, and then put your sum of fourth powers here. Sum of quads? I'm not really sure. Right? So instead of sum of squares, we're raising it up to the squared squares, right? So that's one way of writing it. Another way of writing it is you can make the sigma sign really big, x sub I minus the mean to the fourth power over n minus 1 times s to the fourth power, right? But all of these things are the same thing. And once again, this is really the heart of the idea of kurtosis. And one of the reasons it's to the fourth power is, let's think about it. Remember, it's very concerned about being either on the outside or on the inside of the distribution. Are you on the tails or are you at that peak? And by raising it to the fourth power, it makes everybody matter a lot. And especially if you're on the outside, you matter way more than if you're on sort of the inside. All right. One more thing to the idea of kurtosis. Now, typically, kurtosis is going to be, so for a normally distributed function, let me draw it here. For an approximately normal looking distribution, nice bell curve, right? The kurtosis, if you calculate it with some function like this, is going to be 3, right? And that's so arbitrary, right? Just this weird number. And so what they've done is they've made the kurtosis function so that you subtract 3 from it, so that the normal distribution has a kurtosis of 0, right? Because 3 minus 3 is 0. And so that's how you actually get negative kurtosis. It's not because of this function, but it's because you subtract by 3. So the lowest kurtosis you could get is negative 3. So that's sort of this odd, bizarro thing. I'm not really sure why they decided to normalize it to 0, but my theory is that they thought it would be hard for people to remember, like, above 3 is like something from normal and below 3 is something from normal. So they just make you do it in the formula. All right. So now that we have this like weird correction of subtracting 3, now we could talk about interpreting kurtosis. You already know that a kurtosis of about 0 would mean that you have an approximately normal distribution. Oops, it's a crappy normal distribution there. All right, so that's what a kurtosis of 0 would be. A kurtosis of less than 0, and a kurtosis that's greater than 0 is going to be more peaked, more pointy than normal, right? So something like this, right? So that's a kurtosis that's greater than 0. And we call that leptokurtosis. leptokurtic. It just means more peaked than normal. Now, we could call other things that have a kurtosis that are similar to the normal distribution. We could just say they are similarly kurtotic to the normal distribution, but that would be really long. So we say they are mesokurtic, because you don't have to be a normal distribution to have a kurtosis of 0. Mesokurtic just means it's about the same peakness as normal, right? So that's mesokurtic. Because we can't leave well enough alone, we need to have another for something that's less peaked, or like flatter than normal. And I like to remember this because, you know, mesokurtic, leptokurtic, that always sounds crazy, but meso, I just remember, oh, it's like in the middle, so middle kurtosis. But lepto is hard for me to remember which it is, but that's why this last one helps me, because this one I could always remember. It's called platykurtic, and I think of a platypus and how it has like a flat beak. So platykurtic, that means this is flatter than normal, so smaller peakness. Than normal, right? So that would be something that looks more like this, right? So that's platykurtic right there. So those are our 3 interpretations of kurtosis. Now let's go to our Excel examples and look at kurtosis there. So here, let's click on our kurtosis data. That's the 3rd sheet. And we could look at 3 distributions that I've already put in there that might be good for us to look at regarding this idea of kurtosis. The uniform distribution, obviously the tails are just as fat as the peak, so it's not super peaked. The tails are super fat. Here we have more of a peak, but the tails are still pretty fat. And here we have the thinnest tails, and the peak is higher than the tails are. So there's a bigger difference between the peak and the tails. Handily, Excel has a kurtosis function. So we could put in kurt, right? And then put in our data. I'm going to close that and hit enter. And what we have here is negative kurtosis, where it's flatter than the normal distribution. And I'm just going to drag all of this over here. Here we still have a negative kurtosis because it's still sort of duller than, it's not as peaked or pointy as the normal distribution. And here we've overshot. It's not normal, but it's actually, it's more pointy, it's more peaked than the normal distribution would be. And so if you want to know the precise formula that Excel uses in order to calculate kurtosis, go ahead and just click on Kurt. And here it shows you this is the formula for kurtosis. Now, what they do is they multiply by this crazy looking stuff, but the crux of the formula is still there. It's the distances, the deviations to the 4th power, and also standard deviation to the 4th power, minus 3 multiplied by some crazy stuff. And so that's really the heart of that function, and you can see they use that. Now, if you click on the kurtosis page, we'll calculate it on our own. And so I use this n-1 constant. There are other people who use other things. And what I'm going to do is I'm going to put in n-1 down here instead. All right, and then all of this whole thing, the whole shebang, and then you subtract 3. Bizarre, but true. All right, so let's start with this part right here, the deviation to the 4th power. I just put in this value minus the average of my data, and then all of that raised to the 4th power. And I don't want my mean to jiggle around, so I'm going to lock my rows. But I'm not going to lock the column. As long as I copy and paste down here, it'll just use column A. So I'm just going to copy and paste all of that down here. And here's what I get. Notice that all of these values are positive. And so down here, what I'm going to do is sum them all up. So that's one thing I know I need to do. And then I know I need to divide by n minus 1. So count all of these guys. And then subtract 1. Oops. And that's within my green parentheses there. Multiplied by standard deviation to the 4th power. So that's STDEV of my data raised to the 4th power. And because because Excel knows order of operations, it's going to do that power before it does the multiplying. And then I'm going to close that. And so that's my blue parentheses are closing there, right? And so here we have the sum, this part divided, oops, I just put in something crazy. Okay, this part, the sum, divided by n minus 1 times standard deviation to the 4th power. Now I need to take all of that and subtract 3. So I'm going to put another set of parentheses around this whole thing and then subtract 3. Hit enter. And here I get a negative kurtosis. Kurtosis. It's negative, and so that means it's flatter than normal. And notice that it's not more negative than -3. That's the maximum. And so I'm going to take this whole thing right here and paste it right here. And what we see is, similarly, this is less sort of flat than the one we just saw, but it's still, it's not quite close to normal, but it's more normal, right? Then if we copy and paste all of that over here, and we find here, this is more sharply peaked than normal, right? So that's our kurtosis on Excel. Let's move on to some examples. Here's example number 1. Given that in a particular sample, the mean is less than the median, is less than the mode, what is the likely shape of this distribution? So this means that somehow the mode or the peak is on this side, right? And the mean is somewhere on this side of it, right? So here's the mode, but here's the mean, and the median is somewhere in between, right? So that would mean that since this guy, the mean, is highly affected by outliers, there must be outliers on this side, right? So I'm going to guess that this is a negative skew, so left skewed. And so that means the skewness number should be negative. What about in a sample where the mean is greater than the median, which is greater than the mode? What is the likely shape? Well, we just have to reason backwards, right? So the mode, right, is the smallest, then the mean, and then the median is somewhere in between. Since the mean is pulled by outliers, my outliers must be here. So I'm going to say this is a right-skewed distribution. And so that would mean that the skewness is greater than 0. So it's a positive number. Example 3. If a distribution has a kurtosis close to 0 and a skewness close to 0, what is the likely shape of such a distribution? Well, we know that a skewness close to 0 means that it is basically symmetric. But it could be symmetric in lots of ways, right? It doesn't have to be normally distributed. But with a kurtosis that's also 0, we know that, oh, that must mean that, that the tails are not too fat, not too skinny, and the peak is not too pointy and not too dull either. And so if both kurtosis and skewness are 0, we could very likely think of this as approximately normal. That's probably a good way to guess. And finally, example 4. Sketch a potential distribution that could have a kurtosis of 1. Then sketch over it a distribution that could have a kurtosis of -1. I find the positive one to be easier because to me, I always think, okay, when it's positive, it means it's sort of pointy, right? And then over it, I'm going to sketch a distribution that's less pointy, right? So probably something like that. So that's it for skewness and kurtosis. Thanks for using educator.com.